And so thanks everyone for attending this lightning session. These are talks that were given at the town hall last Friday. And so we're going to hear from folks again today. It's not going to be quite so rushed, and we should have plenty of time for questions at the end. So I'd like to just introduce myself again to the group. In case some of you have not, this is the first time you've logged into these our OOI virtual booth. My name is Jim Edson. I am the new PI for the OOI. I'll be taking over for John Trowbridge. So I'm going to be stepping into John's big shoes. Fortunately, John and the program management office and the IOs are handing me a well-oiled machine. And I'm not going to mess it up, I promise you. And John is also going to, he's been kind enough to hang out and work with me halftime to really make this a smooth transition. So I don't expect any problems. Of course, I am going to want to try to, as possible, improve our ability to collect the data and get it to users, right? So I will be reaching out to the scientific community. I'll be reaching out to federal agencies and of course the general public because they paid for all this. So today we have our lightning talks. We're going to do this in alphabetical order. You can add questions on the chat, and I may ask just briefly for questions in between these the lightning talks, but I sort of expect that we'll have a nice discussion at the end. Okay, but I will ask in case you've got questions on your mind right after the talk. So I'm going to start with alphabetically. Shima. It's Abadi, and she's an associate professor at the University of Washington, Buffalo. And she's going to talk to us about her research that's using the long-term OOI hydrophone data. And I'm going to let you introduce yourself, Shima, like I said, and so you can take a little bit of time here. Go ahead.
Thank you so much. Yeah, my name is Shima Abadi. I'm an associate professor in UW. And before I start, I'd like to acknowledge my PhD student, John Ragland, who is a PhD student in the electrical engineering program here in UW. I also like to acknowledge the funding agency, ONR, for sponsoring this project. So as Jim mentioned, I'm using the hydrophone data, OOI hydrophone data. There are 11 hydrophones at the regional cable array and at the Oregon endurance array. Some of them are low frequency hydrophones sampling at 200 hertz. Some of them are high broadband or high frequency hydrophones sampling at 64 kilohertz. It's a rich data set. We have analyzed this long-term data since 2015. So it's more than 6 years of data. We have analyzed it to characterize the ocean ambient sound. And a couple of years ago, not more than 2 years ago, we looked at characterizing the wind and rain noise at the Oregon offshore and Oregon shelf location, because there are two surface buoys that are keeping a log of wind speed and rain rate. And there is also a hydrophone at the seafloor. And then after that, we looked at all the hydrophone data for characterizing the ambient sound over 6 years. We were able to see a lot of fin wheel vocalizations, lots of earthquakes, shipping noise, many things in the ocean. So really appreciate providing this data set. What I want to talk about today is the project that John is doing. John is looking at only two hydrophone data, Central Caldera and Eastern Caldera. These are low frequency hydrophones. And what we are doing with that data is we calculate the correlation between the signal at two hydrophones, and we take the average over time. And this technique is called noise interferometry. And by averaging in time, if the averaging time is long enough, we get an estimate of the time domain gains function or transfer function of the ocean channel technically. So we can see what time is the time of the direct path arrival, what time is the time of the surface reflection arrivals, and so on, the higher order reflections. So what I'm showing here is technically the noise, what we call noise cross correlation function, which is the output of the noise interferometry technique. And we show time delay on y-axis and time over 6 years on x-axis. And these red lines that you can see here in this plot shows different arrivals. It's a two-way, it's a two-way transfer function. So we see positive time. These are the signals coming from, I believe, from eastern caldera to central caldera, and the negative is signal coming from central caldera to eastern caldera. So we see that direct path is this big peak at about -2 seconds, and the next one is the surface reflection. We also see at the positive arrival, and the next one is the second surface reflection. And if you calculate the average, you may see higher order reflections too. We also see a lot of interesting features in between. We have looked at some of them, like for example, right, this region that you see a very high signal to noise ratio is due to an air gun experiment that happened right over the caldera. So we took advantage of that experiment to get high signal to noise ratio in our estimate. You can look at these two publications if you are interested to know more about the noise interferometry, and I'd be happy to answer any questions.
All right, excellent, Shima. Yes, so do we have any questions from either the audience or even the panelists? Because if not, we'll move on, and I'm sure we'll have time at the end. Okay, so let's move on. Next, alphabetically, is Tiago Bilo, who's a postdoctoral researcher at Scripps at the University of San Diego. He will be talking about the use of OOI Erminger C data, looking at salinity anomalies. So I'm just going to let you take over, Tiago.
Thank you, Jim, for the introduction. So yeah, we use the flunking marine B to be more specific in the Erminger Sea, which is this little star in the left map, right? To study the arrival of what we are calling a new great salinity anomaly in the subpolar North Atlantic, which we found that actively helped to weaken the convection in the Erminger Sea. Now, the Erminger Sea is an area of deep convection that can happen and deep water formation. So it's important that we understand those mechanisms there. So in this map that I built, it's an animation of Argos salinity anomalies. So you can see that this freshwater anomaly, characterized by negative salinity values here, it moves counterclockwise or cyclonically in the subpolar North Atlantic from the Iceland basin to the Erminger Sea. And as it does so, it increases the stratification in the area. So what I mean by that, it increases like the difference between the density in the upper ocean to deeper parts of the water column. So it's in that, and it's what I'm showing in the right panel here, which is buoyancy. Buoyancy is just a measurement of how strong the stratification is, right? And if it's stronger, it's harder for the atmosphere to rob heat from the ocean and impose convection. So the black dots is the buoyancy in the upper 1,000 meters calculated from the flunking marine B. So you can see as this anomaly reaches the and propagates into the Erminger Sea, the buoyancy gets higher. So the stratification gets higher. So it's harder for the atmosphere to force deep convection. And at the same time, of course, if we know that what's going to determine if deep convection is happening is how strong is the atmospheric forcing relative to this stratification. And that's the interplay that we have to look at if we want to see if deep convection is being forced or not in the deep ocean. Saying that, we realize that because of this salinity anomaly between 2016 and 2020, the buoyancy just doubled its strength, essentially, mostly because of salinity. And even though like there were instances that we have, and the size of the bar is how strong the atmospheric forcing is. So if it's very short, it means that the winter times in that particular year was very mild, okay? In 2019 and 2020 is where we have this suppression of deep convection. So we have two things going on at the same time. One, the winter time was really mild in those 2 years compared to the previous ones. But at the same time, we have the enhancement of desertification, right? So we have those two mechanisms going on at the same time. And even though we also found out that even though during those times where we don't have like very strong atmospheric forcing, if this salinity anomaly isn't there in the ocean, the convection would be stronger, and deeper mixed layer depths would be reached during those winters. Yeah, I think that's pretty much it. Jim, I think you're muted.
Tiago, I have a question.
Sure.
How many years of data do you need to really be confident that a trend is happening, that there's been a real change?
Yeah, that's a great question. We were lucky enough that this anomaly, it's strong enough in the upper ocean that we could follow it. Well, it really depends. Now we have like what, 6 years of data, and what we've seen so far, all the trends that we've seen in the flanking marine B or the OI marines in the Armenian Sea is essentially being affected by this anomaly. So it's okay for now to use this for this particular purpose. I don't know if you're thinking about a decadal variability, like longer time scale, longer trends, then you have to have at least 10 years, 20 years of data. But for this particular event, I guess those 6 years is more than enough. We could follow the anomaly, and even characterize pretty well those signals. And
Thank you.
just one more thing, if you compare to other data sets in the area, they're all telling this kind of the same story. And the OI is a good complement like a good additional information in the basin that for this type of variability that we want to describe. So.
All right, very good, Tiago. I'm realizing now, I think I was muted.
You were
muted before. So I'm just gonna add any other questions from either the panel or the audience right now. If so, raise your hand. And if not, think of some good questions. It's really interesting physical oceanography. So hopefully we'll have a question for Tiago at the end. Given that, I think now we want to share the screen so that Rob can get started here.
Cool.
And while you're doing that, I'll introduce Rob. So next up is Rob Fatland, who's the Director of Cloud and Data Solutions at the University of Washington at the eScience Institute. And Rob's going to bring up a screen. And I'm going to let you just start, Rob, and explain what we're showing here.
Great. Is that shared?
I don't
You're
think
good.
You're good? Okay.
Okay, great. So I'm Rob Fatland. I'm a research computing director at the University of Washington, and I have a kind of an informal affiliation with the Regional Cable Array Project out of the School of Oceanography and, of course, the Applied Physics Lab. And this is a quick presentation on some low-level methods. And it has to do with this problem of the last 20 yards of data usage. So if you think about a system or a program like OI and all the data that is collected, the question that I'm interested in is what percentage of that data has been subjected to scrutiny and analysis. And this dates back to my long history back with JPL and synthetic aperture radar satellites and so forth, where you become painfully aware that you can collect a lot more data than you can use. So really what motivated this work, and it's ongoing work, and hopefully it has value to the community, that's the idea, is two questions. The first one is, if I had every single kind of data at my fingertips, and that means like under the thumb of my code that I'm writing, and that data was not bounded by projects. So for example, it could be OOI stuff, but could also be part of, derived from Echo at JPL, or IUS, or GLODAP, or GeoTraces, or MODIS, or Argo. If I had all that data at my disposal, what kind of visualizations could I put together? What kind of insight could I gather from it? And then the second question that I have is, supposing I have this set of tools, how would I go about sharing this with you, right? We're showing kind of reproducibility and the extensibility, the value to the community of solving the problems. Because for me, when I get a netcdf file and I open it up, I have no idea what to do with it. At least I used to not. And so I've done a lot of kind of banging my head on the wall trying to understand it. And in so doing, I've created a kind of a deconstruction process. So I'm trying to model the process of figuring stuff out and then leaving a trail of breadcrumbs so that other people can do that also. So the deconstruction is the documentation. And then this is a three-part solution. So that's the first part, is deconstruct and document. And then the second part is to create a GitHub repository. So you can see my slide here is a bunch of different data types, and those are all from the cabled array. Actually, those are shallow profilers. So they go from roughly from the surface down to 200 meters. And they're just different data types, including discrete cruise sample comparisons with shallow profilers and so forth. But it's a long laundry list of data. It's temperature, salinity, dissolved oxygen, chlorophyll A, FDOM, backscatter nitrate, pH, PCO2, PAR, spectral irradiance, spectrophotometry data, current data, and so forth. And that, setting aside the stuff that Shima talked about with the hydrophones and the seismometers and tilt meters and stuff like that. It's this vast amount of stuff that you can dive into. It's really fun. And this is just my slide here, just kind of an example of some of that. But if I were to go to this GitHub repository, which is linked in the slide, you'll notice that here there is a table of contents, and there's only one Jupyter notebook, which is called biooptics.ipynb, and that's where most of my work has been recently. However, if I go to the notebooks folder here, that works, then there's another 20 or so notebooks here, various stages of development. But the idea then is that there's a lot of stuff here sort of hidden behind this biooptics thing. And then part 3, after we get this repository set up, that I wanted to point out is that there's a tag down here, or a badge that says Launch Binder. If you're familiar with Binder, this is going to be old hat, but Binder is basically a free service that will connect to a repository like this one. It will inhale all the content, and it will create a temporary executable environment so you can actually execute code. And the kind of uses that you can imagine for this are pretty wide, but basically I'm trying to make sure that all the stuff that I create and put in this repository will run under Binder, so that you can actually get that sense of, oh, I could actually execute this code in addition to like staring at the lines of code and how they're decomposing stuff. So you can sort of think of it as like an exploratorium view of the content. This is another view of the repository, and I'm going to skip on to the biooptics. This is like I say, this is sort of the centerpiece notebook, and it starts way up here and it goes on for a long time, and now I've lost my place. What I was hoping to show with my last couple seconds here was the kinds of things that I'm trying to share are, how would I go about taking a profile? So again, this is the surface is up at the top and 200 meters at the bottom. How would I take a profile of temperature and chlorophyll and dissolved oxygen and salinity and temperature and animate that? And I don't know if this is going to translate through the medium of Zoom, but the charts here are dancing around, at least on my screen. So that's the kind of thing that I'm trying to get to, is that end product. And all the steps necessary to build that animation are built into the notebook. So that's where I'm coming from. And I think I'll stop there. You can contact me. I'll go back to my original slide here. You can contact me at this email, but the 2 links are the GitHub link for the repository, and then the binder, which is of course linked by that little badge. So that's what I thought I'd share. And thank you very much for the time. I really appreciate it. And Shima has a question.
Make sure on mute. Thank you, Rob. We are all, I don't want to say struggling, but there are a number of us who are new to this environment with GitHub, and I'm just seeing the amazing things you can do with it, how versatile it is. And I'm hoping that the OOI will, as we're moving forward, we're already taking advantage of GitHub, but I think we're just going to be using that more and more and more. So terrific. That example is just terrific. So do we have any questions, quick questions from, I see one from a panelist.
Shima does.
Yeah, Shima.
Yes, thank you, Rob. That was a great presentation. I was wondering if you ever try to plot or look at the data that you can get indirectly from the CTD data, like a speed of sound that you can calculate based on the temperature and salinity. It would be nice. I mean, in ocean acoustics, the speed of sound is very important in terms of understanding the sound propagation. And what we need to know is if the fluctuation is in the speed of sound is more due to the fluctuation in salinity, due to some freshwater release, or due to temperature changes, or that would be nice to add. I don't know if you have.
Yeah, well, I will just say that like OOI likes to refer to those derived products as level 2 products. And there's nothing preventing us from creating our own little side industry. So I would love to have a motivated example of something like that. Maybe we could talk about that offline afterwards, because that sounds like exactly the kind of actuated data use, as opposed to there's the data, knock yourself out. So totally support that idea.
Sure, we can talk later.
All right, thank you, Shima. Okay, I don't see any other raised hands, so let's move on to our next speaker, which I believe is Melanie Fewings, who's an associate. Make sure I'm not muted. He's associate professor at Oregon State University, and I know Melanie's been working on this quite a bit. She's going to be presenting on marine heat waves in the Northern California current system. So Melanie, I'm just going to let you take it from here. 1 second. And that's the one. Okay, go ahead, Melanie.
Great, thanks, Jim. So I'm going to tell you a little about some work that my group has been doing on marine heat waves in the Northern California current system using the OOI endurance array data. So the background here is that, as you probably know, a series of marine heat waves impacted the Northeast Pacific Ocean in 2014 through 16 and 2019 through 20. But in the Northern California current system on the shelf where Argo floats don't go, the subsurface expression of the marine heat waves is not as well characterized as it has been in the open ocean, even though there's a lot more work to do there as well. So we took advantage of a concatenated data set that our group has been working on putting together on the 80-meter isobath off of Oregon. And for those who are familiar with the Newport hydrographic line, this is from a series of moorings that have been deployed at the NH10 station, 10 nautical miles offshore. But here I'm not talking about the cross-shelf shipboard sampling sections on the Newport hydrographic line. I'm talking about moorings at station NH10 on the 80-meter isobath. And since 1997, 6 different observing programs have collected hydrographic and velocity data, and they're listed there on the slide. But the most recent one that captured the marine heat wave periods was the OOI endurance array. And so we have concatenated these data sets into a single consistent 24-year record. And when I say we, I mean Brandy Cervantes and Craig Rizzian working with me. And we calculated best fit climatological cycles and subsurface temperature anomalies and marine heat wave characteristics following Hodday et al., their definition. And the reason that this is novel is that to quantify the subsurface anomalies accurately, we need a reference climatology that accurately represents long-term average conditions. And so that's why it was so nice to be able to combine the OOI endurance array, and this is the Oregon Shelf mooring location, with these 5 historical observing programs at the same location, so that we have a more than 24-year-long time series to calculate a robust climatology. And that climatology is shown on the right in this figure, in the thick black line. This is a figure that Brandy made. And at the end of my talk, I'm going to put in the chat links to the sessions where Brandy is giving a longer 15-minute talk. And this figure is one figure from that. So you can see that tomorrow for more information. And Craig Rizian and I are also giving related talks. So I'll put that in the chat. But so the climatology is the thick black line, and the 3 rows in the figure are the near surface, or sorry, the surface 0 to 2 meters. Thanks, Jim. The near surface 6 to 8 meter depth, and the near bottom 70 to 80 meter depth data. And each row shows 3 years of time. And in the purple curves are the 2014 through 16 marine heat wave time period. So right where that mouse is in the upper row, you can see that the purple curve, which is the actual temperature, not the anomaly, is well above the thick black climatology, and it is outside the gray shading, which is the 95% confidence interval on the climatology. So there's a very strong anomaly there, and it does qualify as a marine heat wave by the Hobday definition. And then in the red curves are the actual temperature time series at those 3 depths from the 2019 through 21 period. So there are more findings on the slide. I won't read them all to you, but the main things I wanted to point out right now is that we do find that, 1, the warm anomalies, so the difference between the colored curves and the black curve, they differ in timing and strength at the surface, near surface, and near bottom depths in the water column. And 2, the seasonal timing and depth distribution of the anomalies differs between the 2 marine heat wave periods, the purple and red curves. In the summer, there's a lot of up and down associated with upwelling events. But if you look at the winter periods, you can see that much more clearly. So by combining these 5 programs and including the endurance array, we have a 24-year record. So we could soon reach a standard that is used in the climate science community, which is that you should have 30 years of data for a robust climatology when you have these extreme events going on. And the depth variations that we find in these warm anomalies indicate that satellites are insufficient to characterize marine heat waves in this continental shelf region in the northern CCS. And again, we don't have Argo floats here either. So that's why these subsurface moorings are so valuable. Thank you.
All right, thank you very much, Melanie. I'm glad we gave you more time because I was actually able to absorb what's going on here in the right side panel. Really cool work. Any questions for Melanie? I'm just gonna.
I did put the information in the chat about Brandy's and my talks, which are in one session tomorrow, and Craig's talk, which is in the second session, and he'll be talking about the Newport Line hydrographic shipboard data.
And just so you know, Darlene is attempting to gather up all of the presentations at Ocean Sciences that, are either in OOI sessions or use OOI data. And so you might want to check with us after the week is finally up, because we're going to, this is a work in progress, so people can see these things now. But ultimately, it would be nice if we got an accurate list, because one thing about these virtual meetings is things are recorded, and so you can go back and take a look at things. So anyways, it might be, we ask you for your help. If we missed your talk, please just let us know and we'll add it to the list. Hopefully, and then maybe in 2 years' time, when we're hopefully back to in person-to-person or face-to-face meetings, we'll do this ahead of the meeting so that people can use that as a guide for what they want to see. Anyways, so just keep that in mind. We're working on that list. So let's move on to our next speaker. It's Derya Gumustel, something like that. Sorry, Derya.
That's okay.
Jim, sorry to interrupt, but Ed Deaver has a question.
Oh, he does. Please.
Yes.
Ed.
So let's. Here he comes.
Sure. Just a question, Melanie. You'd mentioned there that there's velocity data as well as temperature data associated with these moorings. Have you had a chance to look at, is there any evidence of velocity anomalies that are associated with these heat waves?
So Brandy has been taking the lead on writing a manuscript about the anomalies, and she has been separately looking at velocity anomalies. So there are anomalies. I think that she would be the best person to ask during her talk tomorrow.
Oh, sure.
But I couldn't tell you right now how those velocity anomalies exactly line up with these temperature anomalies in time. But I do know that as much as we've looked at it, it's not a super simple story. And that is definitely a major part of our planned future work.
Great. Yeah, I can believe it's not a simple story. You know, the velocities can be quite noisy. Thank you.
Thank you, Ed. All right. So Derya, I'm just going to continue introducing you. So Derya is a research assistant in the Applied Physics Laboratory at University of Washington. She's also using the Coastal Endurance Array data. And rather than just read it, Derya, I'm going to let you explain to people what you're up to. So take it away.
Thank you so much. I'm really happy to be here. Sorry that I missed everybody's talks on Friday. I'm having a lot of fun watching them now. But I'm Derya. I'm from the University of Washington. I'm a research assistant. My research has been on looking into how looking into low dimensional representations of CTD data, and the OOI has had a lot of really good data for this kind of work. So I've been using data from the Coastal Endurance Array, from the Oregon Offshore Profiler in the California Current System, which is marked by this green star here on in the map on the left-hand side. The general goal of my work is to develop a data-driven workflow to characterize intrinsic seasonal structures in water column data. So I've been using shallow profiler data, which is really high resolution. So we've been smoothing and gridding that data and then applying just straight principal component analysis. You can see the first two components, first two principal components in sort of that middle column on this slide. The first two components from temperature and salinity. And we're looking into these to see if they can capture structures in the water column over depth, but also across time, because the OI collects very good time series data. And so you can see in the bottom of the slide, there are these time series activations of each of these components. And they vary over time, and they're capturing these sort of seasonal cycles. So what has been really interesting is plotting these two activations on orthogonal axes. And on the right-hand side, we can see that we actually get this interesting circular pattern, which separates the observations across seasons. So we've also been interested in applying this kind of method to data from the Washington Offshore Profiler. We're finding similar seasonal separation, which is slightly different overlap. So there are different natural processes driving the patterns in this sort of deconstruction. And we're really interested in learning about what processes exactly are being captured by these components. We're also very interested in pairing this sort of method and data sets with decomposition of echo sounder data, also collected by the OOI in this region that other members of my group have been analyzing. So that's kind of all I have. But thank you so much for listening, and I'm happy to take questions.
Yeah, anyone. I'm going to ask a question because I'm not.
Go ahead, yeah.
Too proud to. What do you mean by, could you just explain what you mean by activation?
Oh yeah, so the principal components, the dimension that we're reducing here is depth. So they span the water column, but they change over time because we're applying principal component analysis to this time series data set. And so each component will have a different sort of contribution to the variance in the data set. And that contribution will change over time. And so sometimes, principal component one will be really largely driving the patterns that we're seeing in the data. And then other times of the year, like maybe it won't contribute as much. And we're finding that these first two principal components at least have seasonally changing, seasonally varying contributions to the data set.
Thank you.
I hope that helped.
Yeah, definitely.
Okay, cool.
Let's see.
Melanie.
We have a question from a panelist. Who's that? I have to look.
Hi, Melanie.
Yeah, I agree with you. I really like that right-hand diagram, like you said. I have two questions actually. One, when you say you smoothed, how much smoothing, what time scales?
Yeah, so the shallow profiler in Oregon makes 9 trips through the water column per day. So it's capturing a lot of really high frequency, like the sort of diurnal patterns in the water column structure. But we're really interested in this work and looking at sort of long-term seasonal trends. So we've been smoothing those out into like a daily resolution of temperature and salinity to sort of see how the thermohaline structure is changing throughout the year on a little bit more of a broad scale.
Interesting. And I was wondering too, if you have looked at whether your two principal components, whether the activation time series might be correlated with a lag, which would indicate that you're trying to capture a signal that's propagating vertically through the water column. Have you looked at that?
We haven't gotten around to correlating them to anything like that yet, but that's definitely on our to-do list. We're really excited to like look into what exactly these patterns correlate to. If you have any recommendations or like ideas, I'd love to talk about it with you offline.
Sure, yeah, I'd be happy to talk with you more about it later.
Yeah,
I've done
really
that in a different setting. So
yeah, well, and
yeah.
your work is also really interesting, looking at marine heat waves, because we sort of tried to pick a time zone here for this work. We're looking at mid 2018 to mid 2019. We're trying to sort of avoid that big marine heat wave that happened, but it's hard to tell like if we actually are, or if, you know, sort of a short-term events like that might be captured by components as well.
And I guess just one other suggestion I would make is if you're interested in the seasonal cycle, you have only 1 year. And so
unfortunately, yeah, the Oregon offshore profiler has very mixed data availability, which is why we're also recently analyzing the Washington offshore profiler. It has several years of data as opposed to just like 1 or 2.
That's right. Yeah. And I was going to suggest that maybe you could complement the profiler data with either this time series that Brandy and Craig have been working on assembling at the NH10 location and do something similar, or it's not quite as far offshore, but the Craig's talk that I linked to, if you want the full water column rather than the 3 or few instrument depths, the Newport Line hydrographic shipboard data sections, Craig has gridded the 556 biweekly to monthly sections from 1997 to present. That's in his talk. And it's an amazing data set, and it could be pretty fun to do this across that section.
Yeah, we've actually met with Craig before about this work, and we had heard about a gridded data set like that. And so I'll definitely check his talk out. It'd be really interesting. One of our goals totally is to get this workflow to a point where we can apply it to other data sets and other locations too, and see what kind of similar or different results we can get.
I'm going to put a link to it in the chat for you.
Thank you so much. I really appreciate that.
Oh, this is awesome. Thank you, Melanie. Thank you, Derya. This is what we're hoping to get, some nice discussion going here. Okay, so alphabetically next is Artash Nath. He's going to shame us all. He's a 10th grade high school student who's using all of the OOI data with other sound sources to look at, you know, ambient noise and such in the global oceans. And so I'm just going to leave it at that, Artash, if you don't mind, and let you explain your presentation. And I think you want to share, correct?
Yeah, sure. Thank you. I'll go ahead and share my screen. All right, hopefully this is good. Hi, everyone. I'm Artash, a grade 10 student from Toronto, Canada. And I've been working on understanding the changes in underwater sound levels caused by human activity during the COVID-19 pandemic. Why is this important? Well, the shipping noise, which occurs in lower frequencies, overlaps with the sounds that marine mammals use to communicate, forage, reproduce, and understand their environment. This can cause stress for marine mammals and can cause collisions between marine mammals and ships, which leads to a decrease in marine mammal population. So I aggregated hydrophone data from over 30 years of hydrophone data from 10 oceanic sites located in the Pacific, Arctic, Atlantic, and Mediterranean. I analyzed this data and calculated the monthly long-term spectral averages for the months in my data. Then I resampled my data and calculated the sound levels in the 63rd octave band, in which amphibolic sound is dominant. To reduce the effect of wind speed in my data, I calculated the correlations between wind speed and sound levels at different frequencies. I found that wind speed only starts affecting sound levels at frequencies above 125 Hertz. Nonetheless, for my analysis, I only used data from days with a Beaufort scale between 2 to 4. So the change that I would be seeing would certainly be because of changes in amphibolic sound only. My results were very interesting. I found that sound levels decreased in the 63rd octave band in all the stations between 4 to 5 decibel in the peak lockdown periods. Because decibels is a log scale, this is an equivalent to 2.5 to 3.2 times decrease in sound intensity during this period. I validated the changes I was seeing with AIS data of marine traffic for each of the areas that the hydrophones were located in. This table shows the decreases in sound levels for all the stations in my study over time for the year of 2020. So it's very clear that the sound levels decreased in all the stations and all the oceans during the COVID-19 pandemic. These changes and decreases occurred at different periods of time. This is because the pandemic originated first in China. So obviously the Pacific Ocean was the first one to be impacted because of the huge amount of shipping between China to North America via the Pacific Ocean. Then the decrease occurred later in around March in the Atlantic Ocean because of the changes in traffic between Europe and North America. Finally, the latest changes in the year was seen in July and August, and this was in locations like Glacier Bay and Cambridge Bay, in which the tourism season is the dominant source of shipping traffic. So to make my analysis more accessible, because analyzing hydrophone data is very time consuming, I created a web app, monitormyocean.com. In my web app, you can choose the location and then see 3 types of analysis for each hydrophone station, including looking at changes in wind speed and amphibolic sound activity. Policymakers can use my web app to plan moratoria on new shipping routes and energy exploration projects during months during the mating months for marine mammals. This is really important because some species of marine mammals, such as the North Atlantic right whale, is already at the brink of extinction, as there are only a few hundred left. Feel free to check out my web app, monitormyocean.com, and looking forward to hearing your feedback. Thank you.
All right, very good. Thank you, Artash. Do we have any questions? Here, I'm going to look at the participant list. Looks like we have a question from, Darlene would like to ask a question.
Thank you, Artash. I'm wondering, the U.S. Ocean Decade has a student component. Have you been in touch with them? Because I think you would be a valuable asset to their work.
I did not know that. Thank you for letting me know. I'll look into it. Yeah, because I'd really like to share this project with as many sources as possible.
Okay, I can send you a link to how to get in touch with them if that would be helpful.
For sure. Sounds great.
Great,
Very
thank
good.
you.
Yeah, excellent. Okay, so next on our list, and I think we're doing great, is Monica Nelson, correct? Yes, Monica's next. Monica is a PhD student at Scripps, and she's also going to be using Armiger Sea data, but in this case, she's going to be creating a heat budget. And so I'm going to stop there and let you explain to the folks what your project's all about.
Great, thanks, Jim. Yes, so as mentioned, my name is Monica Nelson. I'm a PhD student at Scripps Institution of Oceanography, and I'm working with Jan Mastranio and Sarah Perkey. And Tiago has introduced you a little bit into this region, so I'm looking in the same region as Tiago, up in the Erminger Basin between Greenland and the Reykjanes Ridge with OI mooringers there. And I've been using a combination of the moored OI data as well as Argo data from the Remick and Gilson product, a gridded Argo product, and then ERA5 gridded reanalysis data as well, to look at, as mentioned, a heat budget in this region, to try and understand some of the seasonal and interannual variability in the temperature in that water column, and really thinking about how this water column so we know the water column has these big convective, wintertime convective events, as Tiago mentioned, and that happens in the winter when we have cooling, and then there has to be some mechanism for the ocean to warm back up again, because this is a region where it's well known that over the annual cycle, there's more heat lost to the atmosphere than there is gained from the atmosphere. So there has to be some convergence of heat by the ocean in order to balance the heat budget. So my heat budget is centered on the OI mooring and looks at the change from the start of the change over an annual cycle in the temperature in, I've chosen a 1600 meter water column. And so I define my year starting in September, starting and ending in September, sort of based around that. September is sort of when the water column on average is the warmest. And so then I say that any changes in that water column have to be due to either SE heat fluxes at the surface, and additionally due to a horizontal advection of heat, a horizontal convergence of heat laterally into this water column. And I do this for, I conduct this heat budget integrating a monthly time step for 12 months in a year, from 2006 to 2020. And then the plot that I'm showing on the right there is just the average of each of the annual heat budgets. And so you can see that on average, we really have a pretty balanced ocean state over the seasonal cycle. The storage is near zero, and that's the result of a strong amount of air-sea, heat removal through air-sea heat flux, and then balancing that with horizontal heat convergence. But what you don't see in this average plot is that there's a lot of year-to-year variability with these average bars going up and down. And we've been trying to look at, understanding sort of the mechanisms behind that variability. And in particular, there's been a recent mid-depth cooling. So the kind of water column between about 900 and 1500 meters has gotten really cold since 2014, 2015. And so we've been trying to look and see if there's a sort of pattern when comparing the previous warm steady state, and then this new kind of colder steady state that we're seeing this ocean basin be in at the moment. And thus far, the pattern, there is no clear pattern that has emerged. This is still a work in progress, but kind of not seeing any clear regime changes, and not seeing any sort of clear reasons why this cold anomaly has really persisted and not been recovered from. So I think I will leave it at that and be happy to take questions now at the end.
Any questions from the audience? I might ask one. I know convergence is always so hard to estimate, but do you have any ideas on how you might be able to quantify that a little bit, rather than just using the residual?
Yeah, I should have said that the convergence term, so it is just a residual, and we so we can think about that as being like mean geostrophic flow, eddy components, effluent transport. And I did do a bunch of work trying to calculate a mean geostrophic flow. You need the Argo data sets for that to get that lateral gradient to get the geostrophic flow. But it was coming out to be really small when I was estimating that. And so there's thoughts that the eddy component is probably the majority. So one thing that we're thinking about doing is following a method that was developed by Ben in 2013 and 14 to look at the temperatures anomaly at the mooring. And so you can see when you can try and identify as eddies, like warm core eddies, in the temperature time series. and get a sense from that as to how much heat is being brought in by eddies, and in terms of also considering like how much eddy area is there in the basin.
Yeah, because that wouldn't surprise me that it's the eddies. So any other questions? All right, so I think we are last but not least time because Justin's last name begins with an S, and that just happens to be the last on the list. Justin, you're next. Justin's an assistant professor at the University of Hawaii at Manoa. And I really like this because I am a meteorologist, but he's going to be comparing some of the meteorological data from the Southern Ocean buoy against high resolution satellite imagery. So Justin, I'm just going to let you take it from there.
Thanks, Jim. So this work is not just me. There's other folks that have contributed to this from France, Alexi Moose, Bertram Sapron, Doug Vandemark for University of New Hampshire, and Ralph Foster from University of Washington. So I'll just give a brief overview, and then I'll give the strong link that we have with the OOI data. So this work is really motivated by the observing gap, I should say, in estimating air temperature and even humidity over the ocean. And this has a lot to do, if we can get that right, we can actually get to things like fluxes, heat fluxes a lot better. And this is a lot of Jim's work that we're relying on through CORE, these bulk parameterizations, which are very sensitive to the estimation of air temperature. So what we are doing in this work is that we're using a machine learning technique to give us a probability of what category these different SAR imagery look like. So this, we have 3 examples here on the bottom. I'll start over here on the bottom right. This image here has negligible atmospheric features on that, and we're calling this NV for short. And the middle panel then has these streaky patterns, and these are roll vortices that are putting their imprint on the ocean surface. And the last one here on the left is this popcorn looking structure. This is convection in the lower atmosphere. So this is overturning of the atmosphere. So what we're doing then is we're using this convolutional neural network automated version of that to basically give us a probability of these images. And then we're seeing where they map in terms of this Richardson number. Richardson number is given in this equation above, which is basically on the numerator, we have the buoyancy term, and on the denominator, we have shear in the atmosphere. So it's basically a ratio of buoyancy production to shear production. And what we're seeing in the probability of these 3 classes is that they're mapping really well in terms of a Richardson number. And this Richardson number we're computing from a reanalysis data set. And this is quite a lot of data. Just to put this into scope compared to previous studies, we have hundreds of thousands of images that are going into these PDFs. And the gray plots here, gray bars here are all the data combined. So our whole population of satellite observations. And then you see that the red plot here for our NV class is mapping really nicely into a positive Richardson number most of the time. You can see we have a tail here. But this suggests that the atmospheric boundary layer is stable. So this means that our shear production is really dominating. Our wind streak class, the blue PDF curve, you can see that the majority of the data is close to 0, but it's on the negative side. And this means that basically our buoyancy and shear are on the same order of magnitude. And it's slightly on the negative side. So this is basically the balance of these 2 are equal. And lastly, we have the convective case, which is mainly negative, which is unstable boundary layer. So that's really great that we have this match, because we're basically, these image textures are giving us further information about the atmospheric boundary layer. And in particular, we could constrain bulk parameterizations like the core model by basically telling the core model which of these 3 categories we fall into, because the way that this model works is there's a split function basically depending on which category. So we can possibly constrain that bulk parameterizations a little bit better. So now looking into the future, we want to improve our method of basically identifying these images. And to do that, we need to be very rigorous in the estimation of fluxes or of the Richardson number in this case. So for that, we need observations, and there's very few places in the globe that have the information we need to calculate the Richardson number. So OOI is then our great link. So right now I'm showing data from the Southern Ocean Global Array down here, which is a very unique station. And right now I'm comparing tags from my colleague Doug Vandemark and tags from myself. We hand labeled 300 images here, and then we're seeing how they map into Richardson number space. And we don't have a lot of data, so it's hard to see a little bit of a distinction, but we do have corresponding results of what we had with this bulk version we have on the right-hand side using reanalysis data set. So looking into the future, we're going to heavily rely on the OOI assets to basically improve our method here of detection and then mapping these events.
All right, thank you, Justin. I love this stuff. I have to say, when way back in the day when we were using SAR, because there was so few SAR imagery and they're so expensive, you know, we milked one image of the Gulf Stream to death. So we saw, you know, stable side, you know, popcorn convection on the other side. But now there's just, you know, with these little postage stamps of SAR that you can get, you know, doing this sort of analysis, you know, it just is so promising. So keep it up. I know it's hard, and we need to get you more data. I agree. I hope that Doug is sharing the direct covariance data with you.
He is, yeah. So that's
Okay.
the next step too. We're actually comparing some of the more rigorous definitions of the covariance and even like the air temperature. So that's our next steps.
Yeah, and Southern Ocean, what an amazing data set. One thing I'm going to be working on, see if we can't tease out a little more buoy data from the Southern Ocean. But more on that later. So what time we got? I think we're getting close. This is great. So it's about 3 or 4. I'm really glad we had discussion beforehand. We do have time for at least one more question from either the attendees or the panelists before we move on. But I got to say, I feel like this was a nice lightning session. I really appreciate everyone's contribution. We had a good audience. Had some really good questions asked. Tomorrow, actually, I should use the last minute or so. Tomorrow is going to be a nice session I'm looking forward to on education, using OOI data to assist with educational efforts. So if you are able, appreciate seeing you tomorrow at 3 Eastern time for that session. So I guess with that, I don't see any last questions. Again, thank the panelists. Thank everyone for giving their thoughts, and thank everyone for joining us today. And hopefully I'll see you tomorrow. Thank you.
Thank you, everybody.
Thanks, everyone.
Thank you.